Quantum mechanics gets serious. Anyone who is not shocked by quantum theory has not understood it. Niels Bohr. I repeated to myself again and again the question, can nature possibly be as absurd as it seems to us in these atomic experiments? Werner Heisenberg, Physics and Philosophy. Quantum mechanics forms the conceptual underpinnings for particle physics. Certainly, if you want to understand the mechanics of the particle physics, you really have to develop a deeper understanding of the quantum physics. For the purpose of this course, for the purpose of the just understanding the ideas of particle physics, it's okay just to have a sort of qualitative sense. A very crude sense of what quantum mechanics is about. It's a very rich and deep field, absolutely fascinating physics, and I would encourage you to go learn more about quantum mechanics. It's got enormous applications throughout all of the physics and the technology. But I want to talk about the evolution of ideas that led us from classical physics to the quantum mechanics that was developed in the 1920s. That's going to be the topic of today's lecture, right? Quantum mechanics was a theory born out of the desperation. This was a data, and it was in disagreement, clear disagreement with the classical physics predictions. Classical physics was well developed. People really thought in the late 1800s that we had a great understanding, a deep, core understanding of everything, the world, what the world is made of, how it works. Yet, there was this evidence that there was something at some level, in particular when you get down to the level of the individual atoms, that wasn't quite right. It wasn't fully formulated correctly. So, we were confronted with, in certain cases, this disastrous experimental results that just disagree with the theory and had to repair it. So, the early days, the days of Max Planck and Albert Einstein and Niels Bohr were just tentative steps, ideas towards the formulation of quantum mechanics. The word mechanics to a physicist just refers to a description of how things move and why they move that way. So if you have a tennis ball and you whack it with a tennis racket, classical mechanics explains how it's going to behave as a function of time after you hit it, as a function of time, right? The laws of the classical mechanics work just fine when you are describing ordinary object, but they seem to be breaking down when we are talking about electrons or atoms, the constituents of atoms, right? In the early 1920s, German physicist named Erwin Schrödinger was asked to give a little colloquium on these crazy ideas of the Louis de Broglie. The French prince who had first formulated an idea that perhaps electrons should be thought of not just as a particle, but also as waves. So Schrödinger gave this little talk, and an elder physicist in the audience said that he thought all this talk of waves, with the people waving their hands, was kind of silly. If you want to talk about waves, you need a wave equation. This is a physicist's way of thinking. In the 1800s, we had described sound waves and water waves mathematically rigorously. So, let's come up with a wave equation which describes these quantum waves that people were talking about in such a casual fashion. So, Mr. Schrödinger, who was a very smart young fellow, went off and started thinking about this. He was really trying to come up with an equation to describe the wave nature of an electron. The story goes that in the winter of 1926, he went off on a little winter holiday. Didn't take his wife, he took his girlfriend. What a corruption. What's a destruction. His goal was to keep his girlfriend happy and work out a wave equation. apparently succeeded. Certainly, he succeeded in getting a wave equation. He got the Nobel Prize for it in the 1933, 7 years later. Wow. The Schrödinger equation is an equation, so physicists are excited. They can solve it, and what does solving it mean? Well, it's a sort of funny business at first. They are not quite sure what this wave represents physically. It's got something to do with electrons. You could solve for an electron in a cathode ray tube. You could solve for an electron buzzing around in an orbit around a proton, which would be hydrogen atom. Right. The equation yielded quantitative result for things like the energy of electrons, something that you can measure in the laboratory, and it gave correct values. These values were inexplicable by classical models. Niels Bohr had kind of built this almost hit-boot, quasi-descriptive quantum picture, but it wasn't very rigorous. However, now we had an equation, and to solve the equation, you come up with numbers, and they agree with the data, so it's looking good. And the question was, what is waving? It's not a water wave, it's not a sound wave. What is waving? I think this is just a phenomena that things pass through, rather than the object itself. And I don't really have a good answer for that, even today. But in the interpretation, the best interpretation I can give came from a fellow named Max Born, another German physicist. And Max Born, just a year after Schrödinger's equation, came up with what is still today accepted as the best possible interpretation of this wave. It's a probability wave. So what on earth does that mean? Right. Quite right. Imagine, let me draw a wave for you. So it's big in some places and small in other places, like water wave that's tall in some places and low in other places. Max Born says, no, think of this wave abstractly. Where it's big, that's where the electron is likely to be. That's where it's probable to be found. When the wave is small, that's where the electron is not likely to be. So it's not that the electron is traveling along in a wave-like pattern. It's not going up and down. Wow! Good explanation, huh? It's traveling along in some paths, and what we're saying from this wave equation is there are certain places where it's likely to be found, and other places where it's not likely to be found. This probabilistic interpretation of Schrödinger's equation was a key ingredient. It was a necessary ingredient to make quantum mechanics work and describe all sorts of other physical phenomena. Wow! People didn't like it. People didn't like it then, and even today there are plenty of philosophers and even physicists who argue about what this means. Does it mean what we've lost? The rigorous, deterministic sense of science that Isaac Newton introduced us to in the 1600s? These are aspects of the quantum physics that are very hard to grasp, very mysterious, and I'd love to just continue to go into those, but it's really a detour from the course on the practical physics, so I have to lead you to study quantum physics on your own, right? Moreover, the mathematics, right? In order to see the logical connection, perfect truth, right? You are not alone if you find the idea of quantum physics as a little bit disturbing. Albert Einstein never really bought into this idea of the probability. He saw that nature, at its core, had to be rigorous and deterministic. He said, God does not play dice with the universe, and there were lots of people who felt that way. In fact, even Mr. Schrödinger at later time said, Had I known that we were not going to get rid of this damned quantum jumping, I never would have involved myself in this business. So even Schrödinger, who invented the equation, thought that it was some physical kind of the wave, and has people reinterpreted his work. Schrödinger was not the only one developing a quantum theory. There was another German physicist named Werner Heisenberg. Yes, Heisenberg. Heisenberg actually came first chronologically. He was a year before Schrödinger in his publication. Heisenberg had a rather different way of thinking. He was very mathematical, and he said, "Look, I don't want to ask questions about electrons that nobody can see. It's too small to look at an electron or an atom. So instead, let me write down equations that describe things we can see and we can measure. Like the light that goes into our apparatus and the light that comes back out again." Right, quite right. That's something that I have dials and meters, and I can read that stuff. That is physics. So he wrote a mathematics which connected what goes into what comes out, which after all is what science is supposed to do, and he succeeded. Whoa, so savvy. It was very fancy mathematics. At the time, physicists weren't so well acquainted with what's now known as matrix mechanics, and they were very familiar with wave equations. So I think even though Werner Heisenberg came first and was actually successful in his theory, Schrödinger gets a lot of credit because everybody else in the community was able to take his idea and do the math more easily. Since then, people have gone back, and in fact nowadays, when we teach quantum physics in undergraduate and graduate school, we teach both the wave equation and the matrix equations. It was proven shortly afterwards by Schrödinger that they were equivalent. They were mathematically equivalent ways of describing this rather difficult to picture behavior. Right. Mr. Schrödinger and Mr. Braun left Germany during the early 1930s as the Nazi came into power, but Werner Heisenberg stayed behind and in fact became very influential. He was the director of the German program to try to develop nuclear weapons during World War II. There were very interesting stories about these characters, as you can imagine. There is a very recent play, in fact, that talked about what did Mr. Heisenberg actually know. He claimed afterward that he was trying in some sense to sabotage the Nazi war effort, which was why they didn't develop the nuclear bomb. It is an interesting story, but a little bit of a detour. Wow, such a cool guy. Such a great guy, I should say. Quantum mechanics is a very counterintuitive, and we are not going to go much further into details, certainly not into the mathematics, but I do want to leave you with the following sense of quantum physics. Although there are some somewhat mysterious philosophical aspects about the interpretation in terms of physics, in terms of the predicting the result of experiments, this is a rigorous science. You have equations, you do calculations, you check, and they agree with the data, and it agrees well. In fact, this story, quantum mechanics, which was developed in the 1920s, is still used today. It describes the semiconductors and superconductors and regular conductors, and just about any system that involves small objects. Small object is quantitatively well described in the quantum mechanics. So even though Werner Heisenberg wrote down what is now called the uncertainty principle. Yes, uncertainty principle. Yeah. The uncertainty principle isn't just some nebulous statement that, well, quantum mechanics is weird and everything is uncertain. It is in fact a rigorous mathematical formula, and it says, if you know the following quantity very well, then you are obligated to lose information about another related quality. It's a fairly bizarre statement, but it's accurate. It agrees with data, and there have been lots of experimental tests of the uncertainty principle. The uncertainty principle doesn't say everything is uncertain. You can calculate the energy of an electron in a hydrogen atom with extraordinary accuracy. It just says that knowing one thing often compromises your ability to know something else at the same time. This is what is happening in mathematical field too, or scientific field too. If you become better to solving problems, so being a problem prober, you aren't be able to problem finder. It is always a compromising relationship between problems finding and problem solving. It's never you never expand the absolute value of the value of the summation of the numbers of this. So you either problem solver or problem finder. This is what uncertainty principle interprets the describes our everyday life, isn't it? So let me repeat it again. It just say that the uncertainty principle doesn't say everything is uncertain. You can calculate the energy of an electron in a hydrogen atom with extraordinary accuracy. It just says that knowing one thing often compromises your ability to know something else at the same time. So quantum mechanics is developed in the early 1920s, and almost right away it was observed that there was one theoretical or conceptual problem with this new theory, and that was a special relativity. Albert Einstein's reformulation of the sphere and time is not completely consistent with this early version of the quantum mechanics. There is some disconnect, right? The early version of the quantum mechanics, as written by Schrödinger and by Werner Heisenberg, is basically describing objects that are moving slowly. It works great for the objects that are moving slowly. But what about if you have a little teeny object? So you need a quantum mechanics, and it's moving really fast. As for instance, an electron in orbit in an atom, it's both small and fast, and so you should really need quantum mechanics and relativity. Einstein's theory of relativity is most important, practically speaking, when things are going at speed close to the speed of light. Right.